All right, we'll have to go ahead and then begin. My name is Nikolai Kumar, and today we're going to be talking about the VREP simulation environment. Okay, so many of you might have wondered. Actually, I'm also going to be recording this so that because there's a lot of steps, so I'll just upload it onto YouTube, and then you guys can just go ahead and follow it exactly. But how many of you have installed it and downloaded? Installing? That's okay, I have some stuff to say anyway, so. All right. So, the thing is, in robotics, I have this graph here. Whenever you build a robot, it's well, you first start off with a design criterion, right? And then you go ahead and you say, oh, you know what? I sort of designed it. I think it'll work. I'll go ahead and construct it. But then usually what happens is you find out it doesn't work, and then you get angry, and then you have to go back to the design stage, okay? And then you'll bounce back and forth between design and construction. But as it turns out, the time between design and construction is pretty long, arguably. As you know, you had to, I don't know, you have to design the circuit, you have to implement it, you have to test it. So that's where simulation comes in. It's actually relatively easy to make minor changes to the simulation and then run it again and then see what happens. So that's kind of why simulation is a very big part of robotics. Yeah. Last time we did the AAR, a lot of teams just went back and forth between the design and construction stage, especially when it comes to how to behave in the obstacle. You guys still have the obstacle course, right? Yeah, in the obstacle course, they would write something up on Arduino, upload it, run it, see, oh no, we need to increase whatever variable. They would have to go back, try again, find out that they screwed something up, and then this would be just like this repetitive process. The thing is, it takes a lot of time, effort, and it burns lots of batteries, and it's just kind of a pain. So that's where this new simulation environment comes in. How many of you have it installed now? VREP. It's from Copelia Robotics. I can actually go ahead and I'll demonstrate some of the things that this program can do, and then I will show you how to model your car. And I'm going to pretty much have to be sitting down. I don't like it, but it'll be all right. So, when you start your program, you'll get something like this, where you have your scene in this window, and then you can, using the left mouse button, you can pan around, and using the right mouse button, you can rotate the screen. And then you can zoom in and zoom out. Here, there is something called the scene hierarchy, and that shows you all of the objects that are within your environment. And over here we have the model browser. And this model browser here, it comes with a few pre-built parts. So for now, we'll open up I'll just demonstrate something. You guys don't have to follow it just yet. We're going to open a sample scene. Okay. The reason why I'm restarting is I don't know where their sample scenes are, so I have to find out. There we go. So I'm going to open up the EPUG demo. And the EPUG demo is doing something similar to what you might be having to do. It's kind of this robot called the ePuck, and it's following a line and trying to avoid some obstacles. So you can run the scene by pressing the run button right here, and you'll see what happens. Over here, you actually have, this is kind of a custom user interface. We won't be able to do that today. But over here, these three dots are actually the light sensors. And they go white or black depending if it sees a line. And then these over here are proximity sensors. So, and if you're curious to see how this works, you can actually go and just explore whatever they have in here. There's the ePuck, which is an object with a whole lot of sub-properties. There's a bunch of sensors and all of that stuff. But we're more interested in a car type robot, so we can stop this. And you can actually follow along now. In the model browser right here, they have examples, and they have something called simple Ackermann steering. Now, Ackermann steering is what you have on your cars. So we'll open this up. Nope. Actually, let me close the scene first. Oh, yeah, sorry, you click on it and you drag it onto the environment. And it gives you a little bit of information. It tells you that you can actually control this using the arrow keys. So over here, you have some camera controls, right? So you can, when you have this mode activated, that's the panning mode. So let's zoom out a little bit. And you find that this car is quite large. So what we do here is we right click on it, and actually we double click on this little cube right here, and then we click on common, and there is this scaling property right here which allows us to scale it down a bit. And the truth is, I don't know how much or how big it is, so I'll just scale it down to 0.1. Okay. Okay, so this is more of a interactive thing, so if you're ever lost, just shout out and I can tell you exactly what I did. So now that I've scaled it down, this car is a lot more manageable for the environment.
What is the scene? How did you shrink it?
Oh, you double click on this cube. Yeah, to shrink it, and then it gives you a couple of scene object properties. Then you go onto the common tab, and down here there's the scaling button, and then you click it, and then I set about 0.1. So now you have this steering car, and when you click on this run button, you can actually control it. So if you give it if you use the up arrow, it increases its speed, and then if you use the right button, it increases the steering angle. And these lines on here were just there. I don't know, they were already there. They're sort of showing you the center around it which it turns, the turning radius. So you can kind of, I don't know, just have fun with it for a little bit. But this is the basis that we're going to be using to start controlling the car, to simulate your robot. Okay. I would like you to download some pre-made files that I've made, which are based on this Ackerman steering car. And please go to this website and download the zip file. It should be just on the ubcomechatronics.com. Oh, the Ackerman steering is here under models, and then examples, and then there should be simple Ackerman steering. Do you see it? Yeah. So you just click on it, and then you drag it and drop it in your environment. So yeah, please go to this website. There's a link to download some files. And in those files, I actually started developing a script, and it'll be quite useful for you as a kind of a starting point. Essentially, we'll be needing this file, so yeah, please make a point of downloading it. You got it? Okay, you can just work with a partner. You guys have it?
Yeah.
Okay. Okay. So I'm now going to actually, let me show you one more thing while I'm here. If you go into the scene hierarchy, you see here your Ackerman steering car, and over here you have this this page. If you double click on it, it actually gives you the script that it's running. I want to just kind of show it to you because in the file that you downloaded, I modified it. This is essentially how the car is being controlled. And I will actually explain a lot of these later once we get to it. But here is the main loop. And within this main loop, it waits for key inputs, and then it changes the steering angle and the tire rotation and everything. So this is one of the main things that I took in the modified file, and then I removed it to make it more like the car that you guys are building.
Where do you have this file?
Which file? Oh, the modified file? It should be right here. If you go onto ubcomechatronics.com under AAR 2014 or 13, 14. It should be steering dot. Yeah. Oh, your file might not look like this. You might only have the one bump sensor. Does everyone have it? If you don't, just shout it out and I can stop. So when you open this file, you should get something that looks like this. Looks familiar? So what exactly am I trying to do here? I want to give you a simulation environment where you can test your obstacle avoidance logic. Okay, so within your right now you're connecting the motors, you're connecting all the sensors, so and then you're writing the function. So you have one function that says drive motor at, I don't know, whatever RPM, and one other one that says turn all the way left, turn all the way right, and another function that says I'm going to read these sensors. But now, how do you actually combine them? And this is where this program comes in. It allows you to test all of these things before you even implement them on your Arduino. Okay? So essentially, you can simulate the car driving, the car hitting an obstacle, and then what does it do afterwards. And you can, in the model browser over here, if you scroll all the way down, there is this folder called infrastructure. You can expand it, and all the way down here there is something called walls. And depending on your preference of walls, you can set some that are, let's say, 20 centimeter high, and you can just drag and drop them into the environment. And so you can just sort of build an environment for your robot to try and get out of. Okay, so now that we've dropped this wall, we probably want to move it around or rotate it. Okay, so when you look over here, there is this object item shift, which opens up this pane, and that allows you to move this object around. Down here you have the X, Y, and Z coordinates in the world coordinate frame. So depending on how you have it turned, it moves with the world. So it allows you to see which way you want to move your wall. Also, while you're in this moving mode, you can actually drag it and translate it around. Up here you have the orientation/rotation tab. And you can take it and then you can rotate it around. And then I'm just going to drop it into some random location for now. Okay, so now that you've built your environment, well, first of all, let's run it and see what happens. Essentially, the way I've programmed this logic for now, I created a bump sensor, and it starts driving. Once it hits a wall, it hits it in reverse and slightly to the left or right or whatever it is. Okay. So what we're going to do next, we're actually going to create one of these sensors. We're going to create a front-facing bumper. Okay. So in this toolbar right here, you can select Add, Primitive Shape, and we're going to use a cuboid. A cuboid is just kind of three-dimensional cube, pretty much. So as far as here, you have your coordinate system right here, so you can kind of figure out which dimensions you want. But if you don't pick the right ones, you can always rotate it later. So I'll pick the Y width to be 0.1, 1 centimeter thick, and then the Z size I'm going to pick to be about 0.07, so 7 centimeters. And you can add the material density right here, but I'm not quite at that level yet. I just played around for it for a couple of hours. So, all right. So now you have this cuboid in your environment. You can zoom in. And the cuboid also shows up in your scene. Because it shows up as part of your world, it's currently just an object that sits there and does nothing. So the next step will be to position it into our desired location on the car. And the way we're going to do that, let's align it first. If you go down here into your scene hierarchy, you have your Ackerman steering car. You have the front right bump. Okay, sorry. Let's add another object, and this object will be a joint. And there is 3 different types. There is revolute, prismatic, and spherical. We're going to pick the prismatic one because a bump sensor should only be moving in one direction. Okay? You guys know about revolute and prismatic and spherical? Okay. All right. For our case, we'll be using prismatic, but a spherical joint is something like your shoulder joint. It allows you to move around the sphere. A revolute joint is something like something sliding on a shaft, like a bearing. And the prismatic, technically this is also prismatic, but let's assume it's fixed. And the prismatic one is one that moves in one direction, right? Like a bump sensor, right? Oh yeah, if you guys ever have anything, just shout it out, and also feel free to correct me too. It'll be recorded. Okay. So we'll add a prismatic joint to our world. And the prismatic joint shows up right with this symbol in the world. So let's move it a little bit. Okay. So if you look at your car, you have here 4 different prismatic joints. And this one joint called bump front right, and that's the front right bumper. And what we'll do is we'll try to add a front facing bumper. So we'll select, we would like to align them a little bit. So what we'll do, we'll try to align them in the Y direction right here. So we select both of them. And the order in which you select them matters, so bear with me for a second. You select both of them, and then you click on this on the positioning pane, and then you look here for your Y coordinate, and then you click apply to selection, and you'll find that the wrong thing moved. So now you have to reverse your your order of selection. Okay, so now they have the same Y coordinate. If you look at the way that this joint is currently aligned, it's aligned along the Z-axis, so we want to turn it by 90 degrees to have it facing the front. And we click here on the rotation, object item rotate. And then there's these alpha, beta, and gamma orientation angles. And we'll rotate it actually around the world axis. So we'll try and rotating it by 90 degrees around the X. And then you click rotate selection. And yeah, there it is. The reason why it moved so fast is because it rotated around the origin, which is quite a ways around. Okay, so now we want to also align it. We'll have to align it again in the Y direction. And we'll also align it in the Z direction to make them on the same level. Okay, So now, arguably, we would like this to be at the center of our car. So we will select this one and the car and position it along the X direction. Okay, so now we have this bump sensor, which is right in front of our car, aligned with the axes. All right. So now we have to align the prismatic joint and the cuboid together. And we'll probably do that just like. We'll have to apply it in the X, Y, and Z direction. Okay, so now you have it set up like so. If you were to run it, you will find that because they're currently placed in the world scene, they will just kind of drop down and the car will drive over them. And this is not what we want. Okay, so again, the order matters, but we'll put the cuboid as a child of the prismatic joint. So we'll select the cuboid first and then click on the prismatic joint, right click, and then under edit, we'll select make last selected object parent. What this will do, it will bind the cuboid to the prismatic joint so that they're linked together. And now you can see that I'll rename this cuboid and I'll call this, if you double click on the name, I'll call it front bumper. Okay, so now if you run it, nothing happens. So we should go ahead and make this prismatic joint. I'll call it, I'll double click on it and I'll call it front, I'll call it bump front. Okay, so now we select the bump front first and then the steering car and then make last select object parent. Okay, so now this front bumper is actually part of the object. And let's see what happens if we actually run this. As you can see, this object actually moves along this axis back and forth. So it's moving with the car. So now we just have to add a couple of extra restraints on that motion. All right. And the way we do this, we double click this front bumper object right here to bring up this the scene object properties, which talk about the joint. And we'll copy the properties of this front right bumper. So if you click on that one, you see that the minimum position is 0. We'll set this to 0. And position range is 0.05. So essentially, the minimum position goes based from the center of the joint, and the position range tells it how much it's allowed to move. Previously, we saw it move back and forth by like a meter, and that's what we have changed now. The maximum step size is a bit of a complicated parameter. So for now, let's change this to 0. Let's edit the position range. And then the maximum step size, I'll leave this for now here. This one is the maximum step size at which the simulation environment is going to do computations. It's not, just leave it as 0.1 default for now, and we'll see what happens. All right. So if you run it again, you'll find that it probably won't move too much. So one thing we'll do, we'll actually put a wall right in front of it. Okay. And when you click on the name of it, you will see some of its properties shown up right here in the environment. You have the name, the number of selected objects, and there's also this object type and the prismatic, well, it's a prismatic joint, and you also have this p-value, and this p-value is its current position. Now, if you run this system, you'll find that it went from 0 to 0.05. So we can actually visualize that using a graph. And graphs are good to use if you don't know what's going on, because then you can plot the parameters as a function of time. I know this is a lot to take in, but I don't know. It gets somewhere. It'll be fun. Okay, so we add here, we click on the add pane, and we select a graph, which it for some reason drops in the middle of the world. I don't know why it does that, but we'll just move it away out of view. Okay, when you double click on the graph, it gives you here data stream recording list. So you can add a new stream to record. And over here it asks you, it gives you the option for a whole whack load of data stream types. Now we want to record the bumper position, so we go ahead and select joint position, and then objects/items to record. It will only let us choose prismatic joints, or I think just general joints actually. So we'll select bump front, click OK. The object size we'll put to 1 because that's how it works. I found that it I'm not sure why, but I've had bad results with it being 0.1. All right. Now you'll notice that I'm not super proficient at this, but I made the car go, so that's good. All right. So now we have this graph, and every time we run it, it starts to record. If we want to actually see the output, we have to make sure that the graph is recorded. We'll drag our mouse into the world view and then click on view and then associated view with the selected graph. So now we get the following. And then when we press play, you'll see something. Let me stop it. So you can see here the point of impact was around 0.8 seconds. Okay, so let's go back to our front bumper. Right now it doesn't really do much. It just sort of moves relative to how the car makes it move. So we'll try to simulate a sort of spring. And I'm not gonna lie to you. Oh, to get back into the environment view, you click on a default camera and then right click onto this view and then select view associate with selected camera to get back in here. Alright, so you double click on the front bumper, and over here you have the joint mode. If you selected passive, then it doesn't do anything. But we will leave it in torque/force mode, and we will copy the parameters from the front right bumper. Sorry. So when you have this scene object properties, you click on the show dynamic parameters. And you select motor enabled. And over here we have max torque of 10. So you kind of go back and forth and make sure that they have the same values. So here we can select the target position, and we'll select the target position to be 0 for now, which means it'll always try to make it go back to the undisturbed position. And then this is all good. Okay. One other thing In the scene object properties, you'll find that this front bumper is quite long. So we'll set it to its actual length, which is 0.005. And then it changes it. Okay. Also, these simulations you can record later, and these are very good if you have your design presentation, because then you can justify some of your design choices and you can say, well, we made sure that our control logic actually works in simulations before we go out and test it. Just as a cosmetic thing, right now the bumper is, I don't know, just a bland color. If you wanted to change the color, you double click on the cube out front, and you just click here under colors, adjust outside color, adjust ambient component, and then here you have your RGB value, or alternatively the hue, saturation, and luminosity. Those are kind of just different color spaces, but we'll put it to red, just because the other one is also red. Alright, so let's see how this bumper now behaves. Let's put it right here. Essentially what I'm trying to do, I'm trying to get it to hit the front bumper first and then the other bumper. And then to visualize it, you just view it. Okay. Let me maybe change some of these parameters. I'll reduce the maximum step size a little bit. This way it calculates it more frequently, and that's why it's a little bit more accurate about its collisions. And if you compare it now, it's a little bit cleaner than before, but still. The one other thing that I don't really like is that the front bumper is it's a little bit far back, so it doesn't have a lot of room to move. So I will actually have to reposition it slightly. Okay, now it's kind of sticking out, and now we might see a better deflection. I'm going to go ahead and rotate this wall a little bit. Ooh, that wasn't supposed to happen. I'll just anytime you do something, you just Control Z it, and then it goes back to how it was. Okay, so you can kind of play around with that, but the one thing that is important now we have essentially all the components, but now how do we implement the programming? So I'll just doesn't move much. Part of it might also be because of this. I'll set the position minimum to minus 0. There we go. This is exactly what we want. So what I did was I changed the minimum position to minus 0.05 and I gave it a position of 0.5. Essentially, I might have just had it backwards, so it didn't deflect much. All right, so here's what we have. The car drives along, the bumper is at 0, and then once it collides, all of a sudden the position shoots up to 0.0035. Okay, so based on that, now we can actually go ahead and implement some control logic. Let's go back here. If you double click on the Ackerman steering car and this little page right here, it'll bring you the simulation environment. And why don't I spend some time and talk about this whole simulation environment thing. Just like in the Arduino, you have here multiple sections. Okay, you have here this initialization section where you initialize your variable once, and then over here you have the main loop, which is while true do the following, and then it goes through a bunch of if statements, and then down here it actually implements the steering and the driving and all of that. Okay. This I've just copied and pasted directly from the keyboard control model. So this one essentially, given a certain steering angle, how is it going to behave? So we're not going to. You're welcome to play with it, but I'm just not going to touch it. Okay. So let's go back up top here. Here they are retrieving some of the handles and setting some of the initial values. You have this function which is sim get object handle, and then you give it the name of whatever handle you want, and then you'll have this kind of object. And this object will have certain properties that you can call later during your execution loop. So under here you have bump R, which I added. It's bump front right. Let's add the bump front, so we'll go bump F is equal to sim get, and here it starts to actually suggest a couple of things to you. So you can actually take some time and look through all the properties. I guess it, yeah. And then we give it the name of the bumper, which is bump front. All right. So in this very simple model, what I did was I set it into two different driving modes. So I initialized the driving mode as 1, which is kind of drive forward. And yeah, the initial desired steering angle is 0. The desired wheel rotational speed is 0. This steering rotational speed dx, this one was associated with the button presses. Anytime you would push the button, it would change the steering angle by 2 degrees or increase the rotational speed. I think you can just delete it. And from what I understand, I think it auto-saves everything you write. It's kind of a weird type of script where it doesn't have a save button, and if you do something that is wrong, it will behave how it did last time you ran it. So try to not make any mistakes, or if it doesn't behave how it should, chances are you have a mistake in your script. I'm sure this is a very robust program, and I'm sure they have all kinds of checks and balances, but yes, question? Oh, well, you go through it step by step and you look if there's a mistake.
Perfect. I know.
Okay. Within this file, you also get a couple of examples. Some of the examples are how to assign numbers to variables right here. That's pretty standard. And how to also do loops. While true, that's kind of just an infinite loop. It's going to run until who knows when. And then here you have how to make if statements. So you have a condition here, which is if sim_get joint position bump r is greater than 0.01, which means if the right bumper, which we have bump front right, if it's deflected more than 0.01, then you can do something. Okay. You can also just set the car driving to 0, or you can also check if there's multiple sensors hit, or you can check if you're in a specific mode. It's really up to you where you go from here. I just kind of give you a couple of examples. So let's add a if statement that if the front bumper is deflected, that we have to go ahead and, well, drive backwards. Okay. So the way I understand it in this scripting language, indentation is important because there's no brackets. But they do have an end statement, so that might not be important. It's not like Python. Oh, okay, it's like Visual Basic. All right. So our condition will be sim_get joint position. And then it asks for an object handle, and we'll give it bump f. And I don't remember. I think it goes positive. Well, let's try it 0.002 then. So we'll set the current mode to be equal to 2, and then just end. This current mode is kind of something I made custom, because after it checks for any collisions, it then goes on and checks what kind of current mode are you in. Here I just say current mode is equal to 1, then desired wheel rotation speed is forward, and then else if current mode is equal to 2, then well, what I do here, I set the desired wheel rotation to go backwards. I give it somewhat of a steering angle, so to kind of steer away from it. And I also implement this counter, and this is what it does. After a certain amount of time, it goes backwards, and then it stops going backwards. Okay. So let's see what happens when after we implement this. What happens when you run it? Okay, didn't quite. So it didn't go backwards. So now let's look at what happened here. So we can look at this graph 0, which is I'm going to actually do it properly, and I'm going to call it front bumper deflection. Okay. So it never actually hit anything. So let's reposition our car a little bit. All right. All right. So let's visualize what's going on. There's also a way of getting multiple graphs. Not entirely sure how. So if you know, just shout it out. Okay. So the bumper went 0.02. So here what I'm doing is I'm looking at just how much the deflection of the front bumper was, and then I can use that in the if statement.
I think you're missing the bracket after the 0.002.
Ah, there we go. See, and that's why it's not doing anything. There we go. All right, it's still, there's probably more mistakes, so because it does get to 0.002. There we go. So that's pretty much it. I don't know. This is really it. I don't know. I would recommend that you kind of play around with it, because here you can optimize where do you want the sensors. How many sensors do you want? Is 2 of them are going to be good, or will you need 3? Because then you know if it's kind of, I don't know, if you're really digging yourself in, or if you're or if you're just kind of lightly grazing something. You can also experiment with sideways facing bumpers. I guess what else you can do, you can also try to implement the line follower thing. I'm not exactly sure how, but I'm sure if you open up the EPAC example, you can probably just copy and paste whatever the light sensors there are. Yeah, also, before you use this, maybe try to figure out some of the parameters that will make your car behave just like they would your real car. Because with simulations, it's actually a little bit of a tricky thing. In robotics, whenever you have a simulation, it's actually not as good as if you have an experiment. But you shouldn't do an experiment without a simulation first, because you really want to test it on the computers, especially now that computers are so prevalent. And you can, if you look over here, you can find vehicles with very complex number of links. You can have sample robots. You can, put Asimo or something in there, and it has all of them. It has all of the joints and everything. So there's really no reason why you shouldn't try it in simulation first, because you don't want to, I don't know, risk your equipment, by trying it first and seeing what happens. I don't think it'll do anything. Oh, he disappeared. Nope. No, he walks. Huh? Yes, you can. Good question. Just like how you imported the primitives, you can also, there is under File, you can import load model. I think you can import STL files or something like that. Yeah, you would have to kind of play around with it. The truth is, there's not a lot of tutorials on this. Not gonna lie to you. I think this one will be the first one if I put it up on YouTube in English. There is one in Spanish, and it actually is very good. And this is how I learned most of this. So I don't speak Spanish, but it's really very helpful. So I don't know, just try and play around with it. This is just something you can all try, see what happens. And yeah, good luck on your building. Good luck on your exams. Study hard. Procrastinate. Okay.
Awesome.